The tangential acceleration is much easier to find, and we do this again by the analogy of a block on an incline. Again, the angle between the force of gravity and the axis that the tension force is along is equal to the angle between the y-axis and the wire, just like we see on an incline. Again, if I break gravity up into its components, I'm going to now focus only on the tangential aspect of the forces, and I'm going to ignore the forces that are along or against the wire. They're still there, I'm just ignoring them for right now. This is my net force then, that's tangent. It is just force gravity sine theta, just like I have for a block on an incline that is smooth. And since my tangent net force is just Fg sine theta, that must equal ma. Since force gravity is mass times the acceleration of gravity, my masses do cancel out, and I come up with the exact same equation that I have for the tangential acceleration of a pendulum as the same acceleration equation that I have for an incline. Now when we compare a pendulum to a spring, we do see some commonalities. The force that's going to pull the pendulum along its motion depends on the angle. So the larger the angle, the larger the force. Likewise, the force that pulls the spring back to its equilibrium position depends on the displacement, much like the angle. K is a spring constant, which means it doesn't change. It's a constant. Fg is the force of gravity, and so for this mass on this planet is also a constant. So we do see some commonalities between the equation for the force tangent on a pendulum and the force of a spring on a simple harmonic oscillator. But again, if we look at the motion and the accelerations, we do see a couple of key differences. The acceleration on the pendulum never reaches zero and does not point to the center of the pendulum's motion, except when it is at the extremes of amplitudes. Then we can see the acceleration points that way, but once it starts to move, because of that centripetal acceleration, the acceleration gets tilted upwards. Not only that, but because the angle changes with the wire and the y-axis, the angle of this driving force here also changes, so it gets scooted up as well. But for a spring, the acceleration never changes its direction in the point that it only points to the center of motion, the equilibrium position. The acceleration vector also disappears at the equilibrium position because there is no net force at that point. The acceleration equations is, again, very similar in the fact that we have a constant times something that depends on your displacement, be it whether an angle or a position. For the spring, your spring constant and mass are both constants. So that's like a constant times your displacement. One of the things, though, that is unique about the sine function, though, and it allows us to think of a pendulum sometimes as a simple harmonic oscillator, is the fact while that the sine of an angle is not a linear function, as you compact down your interest to only 15 degrees, we can see that the sine function looks very linear. So here we have our full sine function from 0 to 360 degrees. If I focus in on just the first 90 degrees, I see this looks a little more linear. And in this very first 15-degree increment, it looks very linear. It's not. We have deviations, but it is so close to being linear that we can just simply pretend that it is. It's not completely correct, But when you're 99.9% correct, people often say it's good enough. And so we're around that type of percentage many times when we are dealing with a simple harmonic oscillator where the angle of interest is less than 15 degrees. Once you cross that threshold, it becomes very obvious that this force is not going to be linear with your angle, and everything cannot be used from that point on. The force tangent on the pendulum then acts very much like Hooke's law. Here we have Fg sine theta. Here we have the absolute value of negative k delta x, and they look very similar. This one is linear, and this one is almost linear. I need to stress that it's almost. It looks so linear that it's going to be considered to be so, but it's not. And this is where people get confused going, well, if it's linear for the first 15 degrees, why is it not linear afterwards? And the truth is, it was never linear in the first place. It was just close enough that we're willing to pretend that it is. But this is why pendulums will have a limitation with pretending to be an oscillator. And that limitation is the angle. It needs to be less than 15 degrees or 15 degrees at a maximum for this approximation to work. A spring, that's another story. Unless you overstretch the spring where you start to break the spring, you can always use that as a simple harmonic oscillator.